All right, let's work on the 3.5 class activities. We're going to find the general solution using the shortcut that we just developed. There was that box. Okay, so I need lambda and I need v1 in order to plug into the general solution of the system, right? So I know that y general is e to the lambda t v naught plus t e to the lambda t v1. So I need to know lambda and I need to know v1. Lambda I get by taking the determinant of a minus lambda I and setting it equal to 0. So this is the determinant of 2 minus lambda, 4 minus lambda, 1 negative 1. So let's see, I multiply this out, I get 8 minus 2 lambda minus 4 lambda is negative 6 lambda plus lambda squared plus 1. So lambda squared minus 6 lambda plus 9 equals 0. And I get lambda minus 3 squared equals 0. So that means lambda equals 3 is my only eigenvalue, and it has multiplicity 2. So I have a repeated eigenvalue. And I'm working on plugging into y general here, which means the other thing I need is I now have lambda, and v naught is x naught y naught. v1 is calculated with a formula. So v1 is a minus lambda I v naught. Okay, and now I know lambda, so I put it in. Lambda is 3. So I have a 2, 1, negative 4 minus 3i, which is 3, 0, 0, 3. So I'm going to write it out. I can't keep it straight in my head. There's a minus 3 lambda is 3, 0, 0, 3. And I'm going to do all of that times x naught, y naught. Did not leave enough room to do this. Okay. So this is going to be 2 minus 3 is negative 1. 1 minus 0 is 1. Negative 1 minus 0 is negative 1. And 4 minus 3 is 1. Times x naught, y naught. I get negative x naught plus y naught in both entries. So that's my v1. So then I'm going to plug in why can't I erase this? Come on. There we go. All right, I'm going to plug into my general formula here. Y general is e to the 3t v naught, which is x naught, y naught, plus te to the 3t times v1, which is negative x naught plus y naught, negative x naught plus y naught. So that's my general formula. And then to find the particular solution, I'm going to plug in this as x naught and this as y naught. So my general solution will be y equals e to the 3t times 1, 0, x naught, y naught, plus te to the 3t times negative x naught plus y naught. So that would be negative 1 plus 0 is negative 1. So the general form of the solution to a system that has a repeated eigenvalue can tell us something about the qualitative behavior of the solutions. So both of these terms, this term and this term, are dominated by an e to the lambda t. So if lambda is negative, all solutions will tend towards the origin, right? Because then e to the lambda t, if lambda is negative, that's exponential decay, and everything's going to go to 0. And as it turns out, they're going to tend towards the origin in a direction that is tangent to the straight line solution. And if lambda is positive, the solutions all move away from the origin. Everything is growing exponentially in a direction that is, again, tangent to the straight line solution. So these are some typical phase portraits. Tangent to the straight line solution as it leaves the origin. It leaves tangent and then sort of swirls around and ends up parallel to the other side of the straight line solution. And then here we have a sink, and the solutions all come in tangent to the straight line solution. Okay, so to sketch the phase portrait, we need the straight line solution. So I need to figure out the eigenvector associated with the eigenvalue of lambda. So my matrix A was 2, -1, 1, 4. So A times V equals lambda, which is 3 times V. And you get 2x plus y equals 3x, or -x plus 4y equals 3y. Either way, you get y equals x. So an eigenvector would be 1, 1. A nice easy one. So we draw that in the phase portrait by connecting 1, 1 to the point 0, 0. There's my straight line solution. My eigenvalue was 3, which is positive, so solutions point away. Now, I know that all solutions are going to leave the origin tangent to the straight line solution. And the question is, do they go tangent here or tangent here and then swirl? So I'm going to pick a point sort of close to the origin, like maybe -2. No, I kind of want it to be closer, like -0.5, -0.5. Like right here. And I want to see, is it swirling in that direction? If it's anything other than a vector that kind of goes like that, then I'm still not sure what's happening, and I'll pick another point. Okay, so I'm going to take my matrix A, 2, -1, 1, 4, and multiply by -0.5, -0.5. So I get -1 minus 1/2, which is -1.5. And then I get 1/2 minus 2, which is -1.5. So it's going to move left and down. So from this point right here, we're moving left and down, which is that direction. So it looks like my swirl is leaving the origin tangent to the vector in this direction. And then eventually it will sort of swirl around and end up parallel to the other piece of the straight line solution. And then it's going to do a symmetric thing over here. All right, so now we have a phase portrait. We want to sketch x of t and y of t graphs of the solution that satisfy the initial conditions 1, 0. So I'm going to put 1, 0 here. That's my initial condition. And it must be that I would have a solution that does something like that. So from 1, 0, it's probably just going to be heading down and left. So for x, it's starting at 1. And the x values are moving left, which means they're just going down. Actually, they move, the x values, if you start here at 1, they kind of are moving a teeny bit to the right, and then they're going to go left. So this might go up and then down, which that is right and then left, the x values. So this is x of t. And then y, do this in another color. If you start here, the y value at 1, 0 is 0, and these are strictly moving down. There's no like up and then down, they just go down. So this has to go something like that. Okay, so this last thing, very rarely with a repeated eigenvalue, it happens that every vector is an eigenvector for the system. And when this happens, all solutions are straight line solutions, and we classify the origin as a star sink or a star source. You can recognize this case when A equals lambda I. So take note, because the last homework problem tonight falls into this category. An example of a linear system in matrix notation where A equals lambda I if lambda equals 4. So A has to be 4I, which would be 4, 0, 0, 4. So my system would be y prime equals 4, 0, 0, 4, y.